So welcome everybody. Um, Early in the morning in Australia and late evening in Virginia. So today we'll be having Brandon Kennedy from the University of Western Australia, who heads the Bright Lab at the Harry Perkins Institute of Medical Research. And he's also a co-founder, I believe, for a oncology medical company, Onco OncoRes Medical. He has a very deep background in optics and has developed and his PhD on nonlinear polarization rotation in semiconductor optical amplifier. His current research really aims to translate a lot of optical coherence tomography, and particularly today he's going to talk about his depth of work from his group on optical elastography and range of application in cancer research and tissue engineering. He's gotten quite a fair bit of awards, and lately in 2019 got the Western Australian 40 under 40. You're that young, Brendan.
I was then.
That's a good thing. So we will hope that today we hear a lot about how to measure tissue mechanics using optics. So just let Brendan take away.
Thanks, Steve, and thanks, Jen, as well for organising this and inviting me to speak. It's a great opportunity to share the group's work. I should also, just following on from what Steve said about the company, I should disclose that some of this work that I'll present is funded by OncoRes Medical, and I do have a financial interest in that company. So yeah, so elastography broadly is a set of techniques using a range of different imaging modalities to measure mechanical properties of tissue. It's pretty well established using ultrasound and MRI, where it's used clinically in areas such as scanning the liver and breast screening, and it's commercially available for most of the companies in those spaces. The application of elastography in an optical context, particularly using OCT, is more recent, but it offers the advantages of increased resolution, ideally down to 2 to 10 micrometers, but of course only to a limited penetration depth of 1 to 2 millimeters in dense tissues. So I think it's more niche applications than the other forms of elastography. So we've been working on this for a number of years, and today I wanted to give you a kind of a summary which covers the spectrum of the work that our group does, but I'll roughly spend about half the talk describing the technique itself and the technical aspects of it, touching on things like the signal processing techniques we use to measure deformation and strain, the mechanical models we use to estimate elasticity, and also how we go about determining spatial resolution in the variant of OCE, optical coherence elastography, that we use, which is a compression-based approach. In the second half of the talk, I'll then describe some of the work we've been doing to perform margin assessment in breast conserving surgery, and just touch on something which is a little bit more recent, but something that we're accelerating quite a lot in the group, is to try and apply this technology to mechanobiology. So the main steps in OCE are outlined on this slide. So first of all, we have some form of mechanical load applied to the tissue. I'll describe the various forms of loading that you can apply in subsequent slides. You then need to image the tissue, ideally before and after this deformation has been applied to extract the displacement or deformation. We then need to have, from continuum mechanics generally, some model of that describes the deformation of tissue and how that links to material properties, mechanical properties, and that allows us to plot at each pixel in the image the mechanical property. Usually we plot elasticity, and that's transformed into a 2 or 3D image, which we call an elastogram, borrowing the terminology from ultrasound and MRI elastography. So, as I mentioned on the previous slide, we base our technology, or the optical technique we use, is OCT. So OCT is now quite prominent in particularly in scanning the retina, increasingly now used in cardiology and dermatology, and researchers are applying it to a range of other areas. So it uses a scanning Michelson interferometer with a low coherence source, providing the depth sectioning to allow us to section the tissue at a resolution that's determined by that bandwidth of the source. And typically you can get down to 2 to 10 micrometers. Once you start to get below 2 micrometers, you're into the realm of optical coherence microscopy, which is essentially the same technology, but just a higher NA, where you can get down close to submicron resolution. So this slide here illustrates the original version of OCT, which was called time domain OCT, where we scan the reference mirror, and then you have the path lengths matched to within the coherence length of the light source, allowing you to effectively optically section through the tissue. This variant allows you to scan A-scan rates or depth scans over a couple of millimeters, up to several kilohertz. That was quite slow. So more recent versions, and what we use, what I'll talk about in the rest of the talk, is Fourier domain OCT, which has two variants, the spectrometer-based approach, which we use, or a swept source approach. So the idea here is that you replace that scanning mirror that allowed you to section through the tissue with a static reference arm mirror, which you now perform spectral interferometry rather than time domain interferometry. So according to the Wiener-Khinchin theorem, the spectral fringes encode the depth from which the light is backscattered. So if we record these spectral fringes on our spectrometer, in our case, perform a Fourier transform, the amplitude of that signal is the structural OCT image, illustrated in grayscale here, which is used by the majority of the field. But for elastography and also angiography, as well as other variants of OCT, we can access the phase of that complex signal, which is derived from the Fourier transform. The important thing about this phase information is that because it's derived from the speckle coming from the sample, it's effectively, we have no information from it per se, other than the fact that it's temporally invariant. So if we apply a deformation or displace our tissue over a small range, the changes in this phase map encode the displacement. So in our case, we acquire two B scans, two-dimensional images, and then through knowledge of the central wavelength and an approximation of the refractive index of the tissue, we're able to get the axial deformation. And that's important for elastography as well, is that it's effectively a Doppler type technique. So we don't have access to the lateral deformation, which imposes some limitations on elastography. So this allows us to, with phase unwrapping, to measure displacement ranges of several microns to a sensitivity on the sub-nanometer scale, dependent on the OCT intensity. There's a link between the two. So using most techniques, there's also originally speckle tracking techniques were used, where you actually use the structural image and track the motion of speckles. But that actually degraded the resolution quite a lot, because you need to look over a certain window size, and the dynamic range of the measurement is quite low. So the majority of OCE techniques use the phase-sensitive approach that I've described. So this slide summarizes some of the main optical elastography techniques. So as well as the OCT-based approaches, of course, there's Brillouin microscopy and others. Brillouin is probably the most prominent. And this figure here just illustrates the spatial, or the frequency range at which we're probing the tissue in these various approaches. If we focus on the three main OCT approaches, what we use is compression based. So this is quite a low frequency deformation to the tissue. So we assume that there's no wave propagation. The other main approach is actually transient OCE, where you apply a kind of a local pulse of energy to the tissue. That could be acoustic radiation force. It could be laser excitation, or it could be an air puff in the case of the cornea. And that induces a wave propagating across the surface of the tissue. Through a particular mechanical model, you can relate that phase velocity to the elasticity of the tissue. In the standing wave case, you allow the excitation to extend to the boundaries of the tissue. You get reflections and you set up a standing wave. Again, you can use a different mechanical model to extract elasticity in that case. We decided to use compression OCE, which is probably the most simple technique to implement from a mechanical point of view. We make an initial contact, which we call a bulk strain or preload to the tissue of about 5 to 20% strain. Really, the only requirement there is we make full contact with the tissue. We then use a PZT actuator to induce what we call a local or perturbation strain, and that's on the scale of 2 to 20 micrometers, so more on the scale of what we can detect with the phase-sensitive approach. We then can map through this deformation the local strain and the local stress, relating them together in simple Young's modulus formulation allows us to extract the elasticity. One of the reasons we focused on this is that it enables, it more easily enables the development of compact imaging probes, which were important for some of the applications in surgery that we wanted to look at. The main reason for that is that the deformation and the optical beam are in the same axis, so it facilitates a compact imaging probe. When you've got these wave-based approaches, which are very elegant and work quite well, but the problem is that you need to detect the propagation kind of off the axis of the optical beam. The advantage of some of these wave-based approaches, however, is that you can do a non-contact approach. So a lot of colleagues in the field are looking at applications in the cornea, for example, where you don't want to physically make contact. So these techniques are suited there. So really, it's a case of choosing the best technique for the application that you have in mind. I'll go into more detail on how we do this in the next slide, but just simply put, it's if you're familiar with standard compression testing, like an Instron test, effectively what we're doing is something similar to that, but we're using the OCT signal rather than a translation stage to measure the strain in the tissue. That enables us to measure the deformation spatially resolved at high resolution in the sample. And we're also not using a load cell, we're using the actual OCT signal to measure the stress as well, which I'll describe in more detail. But this is quite a simple approximation. We're just saying, hey, we measure the force, we measure the strain, we put them together and we get elasticity. But of course, when you deform a tissue, for example, which is typically an incompressible object, you really need to consider this fourth order tensor where you've got the stress and the strain as both second order tensor. So even if you apply an axial load to your sample, because it's incompressible, it will expand in the lateral direction. So you need these 9 components of stress and 9 components of strain to fully describe the deformation in the sample. But that results in 81 elasticity constants, which is both computationally very complex and also doesn't lend itself well to straightforward representation in an image. So in the field of ultrasound elastography originally and MR elastography, they made a number of simplifying assumptions, namely that the tissue is linear elastic and isotropic. And in our case, we only measure the axial displacement. With those assumptions, we can reduce the tensors to just these single components where we measure the axial component of stress and the axial component of strain, mapping them into images and relating them together, we get the elasticity. It works well in many cases, but there are a number of artifacts that these assumptions bring into the technique, which I'll also describe, and as well as some of our attempts to relax those assumptions to get a more complete picture of the technique. So in the initial case, however, we and many others, and still many people do, is just image strain. So in the case of just imaging strain, you need to assume that the stress is uniformly distributed throughout the sample. In that case, then you can relate the strain to elasticity. So I'll describe that first and then go on to describe how we also measure stress. So as I've described previously, we measure two B scans. We get the phase maps. We apply a deformation using a PZT actuator between the acquisition of these 2 B scans. We then map this 2D displacement map. This is experimental data from a silicone phantom with a rigid inclusion, small inclusion, and a softer surrounding material. So you can make out the inclusion already from this map, but you also have a change in displacement with depth in the sample. So we need to estimate strain to have a more robust measurement of the mechanical property. So if we look at a trace of the displacement through the inclusion, we see that it's really the change in the slope of this displacement trace which identifies this inclusion. So what we do is we use linear regression on this data to map at each pixel over a range of about 50 to 100 microns. We measure this slope, which we call local strain. If we do that at each point in the 2 or 3-dimensional space, we can map these strain images, where now you see, in this case, you've got the very low strain in the inclusion, because its displacement with depth is quite constant, meaning it's not deforming, it's just translating, whereas the softer surrounding material has deformation induced to it, which gives these strain values. We can get strain sensitivities down to 10 microstrain, and as I mentioned, the fit range is typically 15 to 100 microns. What really limits this fitting range? Of course, we'd like this to be this range to be as small as possible. That would lead to the highest resolution. The challenge is that when you've got speckle and OCT images, in dark speckle, where there's a low OCT intensity, your accuracy in the measurement of displacement is quite low. So we usually need to perform this fit over several speckles. Then this just illustrates how we can do that in 3 dimensions as well. So it's a 3 spatial dimensions where we're mapping the axial strain at each pixel. This is a contrived phantom case, where early in the development of this, we felt it was important to demonstrate that we had some additional contrast over OCT. So we made this phantom where we matched quite closely the optical properties of the inclusion with the background material, and varied the mechanical properties, and you can pick out these inclusions quite nicely. So now I wanted to speak a little bit about spatial resolution, and this slide kind of gives away a kind of I think an error that we made earlier on in the development of this technique, where we say that the OCT image resolution is 7 microns roughly in the axial and 11 in the lateral direction, determined by the light source and the optics in the system. And we then naively assumed that the axial resolution in OCE was a convolution of the OCT resolution with that fit range, and the lateral resolution being determined by the OCT system, the optics. And that's true in what we call the system resolution. But on the next slide, I wanted to highlight that in addition to OCT and the linear regression or the signal processing, which again we feel is accurate in terms of defining what the resolution of that system is, but kind of maybe unlike other forms of imaging, the sample actually has a really important impact on resolution in elastography. So because of that, we expanded our definition of resolution to what we call feature resolution. And really what this captures is that because mechanically the tissue is coupled, depending on the size of features and the mechanical contrast between features, you can have a variable resolution in your image. So for example, if you've got a very rigid tissue, that might limit the deformation of the softer tissue around it, because when you apply the deformation, the stiffer material can act effectively as a kind of shield to the deformation that you're imparting, and limiting that deformation can mean that you have a larger gradient in your deformation than you would assume from the simple model that we use. So to try and get a more accurate measurement of resolution, we decided to, from our phantoms, our inclusion phantoms, where we have variable stiffness features embedded in the softer material, we looked at a step response in strain across that boundary. Now, our assumptions are that that's a step change, that you've got 2 different elasticities here. We know that because we made the sample, but you can see when you look at the strain that you've got this gradient in the response of the system, this kind of response as a function of distance. So we measured the boundary across, we measured the strain across this boundary and differentiated this to get what's effectively an OCE point spread function. And we then used this measurement, the full width half maximum of this point spread function, as a more accurate measurement of spatial resolution in this technique, where we model this as a convolution of the OCT signal, the signal processing, but now also the mechanical deformation of the sample. And so with this kind of idea, we started to look at how this measurement of resolution varies across the axial and lateral boundaries of your inclusion. And we also simulated this using a linear systems theory for the OCT signal, and also for the signal processing. and we modeled the deformation using finite element analysis, and then got the convolution of those in simulation and related that to experiment and got a pretty accurate correspondence. So what you see here, if we look at the experimental data, is that as a function across the axial boundary, you have a variation in this resolution from around 100 to say 175 micrometers. So what's happening here is that in the middle region of this inclusion, the ability of the silicone above the inclusion to deform either side is limited by its adhesion to this stiff region. So when you compress the silicone, in order for it to deform axially, it needs to expand laterally because of its incompressibility. The Poisson's ratio is close to 0.5, but the fact that it's physically bound to the stiffer material limits the ability for that to happen until you get to the boundaries of the inclusion, at which point the softer material is now expanding into unrestrained softer silicone, and so you have this sharper transition between the two regions. Also, we see that we've got these large regions of quite low strain kind of in the corners. What's happening there is that as this silicone above the inclusion deforms, the displacement, the deformation is mainly in the lateral direction, which we're not sensitive to in the simplest phase-sensitive technique. So we get this artifactual measurement of low strain. And this is the same kind of artifact that's visible in ultrasound elastography. And in that field, which is again more advanced, they train readers to radiographers, radiologists in interpreting these artifacts. But of course, it can lead to erroneous interpretation of the data. We also look then at a function of the as a function of the inclusion size, and we see in both again the axial and lateral directions that as you make the inclusion bigger, you start to get a degradation in the resolution, again because of this effect of a limitation in the ability of the material to expand. It starts to kind of flatten out at around 1 millimeter, and that's because it's now approximating a kind of an infinitely large sample with respect to the region probed in the center of the inclusion here. So this is just one. We've spent quite a lot of time, in addition to the applications I'll talk about, we've spent a lot of time trying to understand exactly how the parameterization of this technique and how it works. So we've looked at sensitivity and accuracy, contrast, dynamic range, etc. But I just wanted to talk a little bit about spatial resolution here. So given that we've got these artifacts, and sometimes you need to live with them in clinical applications where you need to just scan rapidly. If you don't have 100% accurate measurement of strain or elasticity, it might not matter once you can distinguish, say, tumor from surrounding tissue. But we wanted to be able to make those kind of sacrifices to image quality from a point of knowledge or from an informed way. So we started to develop techniques, in this case, strain tensor imaging, which instead of just assuming this axial component of strain, we developed a complex correlation-based approach to measure displacement, which enabled us to measure the three components of displacement, the three spatial components of displacement. And then we can measure strain using similar linear regression approaches to extract the entire tensor. And one artifact I'll highlight here that this helped us to understand was, this is an axial strain map of, in this case, it's a silicone phantom again, but in this case, we've got a cavity, a hollow region in the center. We noticed that, and usually for compression-based approaches, the strain is negative because the sample is getting shorter. But in this case, we see that we've got a large positive region of strain above the inclusion, which wasn't physically meaningful from our mechanical model. But what's happening here, if we look at the three components of displacement, is that as you apply the deformation, effectively this cavity is collapsing on itself. So above the cavity, you see that you start to get strain in the opposite direction to the direction that you've applied the mechanical load. So when you have the full picture, it makes complete sense. But when we're only looking at this axial strain, we can be tricked. Having the all components of strain also enabled us to map for the first time the compressibility of the sample. So here through the dilatation, we're able to map make a map of the regions of the sample where this where the region is compressible. So this is potentially extendable to tissue, where you could identify cavities probably quite accurately, just looking at this change in the compressibility of the local compressibility of the sample. So all of what I've spoken about so far is related to simply strain, but of course, if we want to measure elasticity, we also need to measure the stress. Now, usually stress is measured through a force sensor, a load cell, but the problem there is you get one bulk measurement of load. We want to have the spatially resolved stress, and also it needs to be on the same scale and coupled with this strain that we measure. So our solution to this was quite simple. We took a compliant region of silicone, similar to what we make the phantoms with. We placed it between the imaging window, which acts as a compression plate, and the sample. And this is a little bit like the Princess and the fairy tale, where above this stiff region, as you compress the silicone, you have more deformation, larger deformation in the compliant transparent silicone. So we can measure the strain in this silicone on top of the sample. In order to get stress, we know the material properties of this silicone, so we can relate the experimentally measured strain to the stress in the material and then make a map of stress across the surface of the tissue. So now we can relate both together, the stress and the strain, and make these maps of elasticity, where in this case, we look at invasive ductal carcinoma and we see a much greater elasticity in the cancer compared to the surrounding stroma. And we highlight as well that this is much greater contrast than you can see in the OCT image, where just based on the optical contrast, you can't really distinguish the tumor from the surrounding stroma. I'm just conscious of time, so I might go through the next slide a bit more quickly. This is just to say that we also developed a technique to measure the full stress tensor. This is based on the inverse elasticity problem. We use an iterative approach in collaboration with Assad Oberoi in particular in University of Southern California. And this allows us to effectively remove all of the assumptions and get a much more accurate measurement of elasticity, albeit with a lot more computational time. But this improved the resolution and the sensitivity dramatically. But as I say, I'll just move through because I wanted to get to the application side. We've applied this to quite a lot of different areas, but I'll just speak a little bit about the tumor margin assessment work and the mechanobiology work. So our application, or our goal with breast cancer, is to focus on breast conserving surgery, which is now accounts for around 2/3 of breast cancer surgeries in the US and Australia, for example. This is where the surgeon removes the cancer and ideally a rim of healthy tissue surrounding the tumor. The problem is that at the surgery time, the surgeon doesn't have a good tool to determine where to stop cutting when they've got all of the cancer or not. What they're aiming for is this negative margin, where they've got the tumor encapsulated in non-cancerous tissue. But in 20 to 30% of cases, the cancer will protrude to the edge. And this is correlated with a strong likelihood of recurrence of the cancer. So if this happens, there'll usually be a second surgery where the surgeon goes back to re-excise. And at that point, you've got scar tissue and it becomes very complicated to know where the cancer starts and ends. So I think it's widely accepted that new tools are needed for intraoperative margin assessment. So we thought tumor is known to vary the stiffness of tissue. This application requires micro scale measurement of stiffness, and also the limited penetration depth of OCT is not really an issue here, because large meta-analyses in breast cancer have shown that once you can determine there's no cancer within around 1 millimeter of the excised specimen, if the patient gets radiotherapy, then there's no increased likelihood of that's sufficient to deem the margin clear. So what we did, we need to scan large regions of tissue, ideally centimeters wide. So first of all, we developed this OCT technique just to mosaic 16 by 16 millimeter sub-images, partially overlapped, to get these 4.5 by 4.5 centimeter OCT images. We can then map those or correlate those against histology. And we can see from OCT that you've got really nice contrast between adipose tissue here and the denser tissues. But once you're within dense tissue, again, as I mentioned on the previous slide, it's difficult to distinguish tumor from stroma. we overlay the elasticity on that, and we sit down with the pathologist who helps us to interpret these H&E slides, we can see that the cancer corresponds quite nicely to where we have elevated regions of elasticity. We first did this on a bunch of mastectomy specimens because we were able to do the histology in the same plane as our en-face image, which was facilitated for this close co-registration. And also, initially, we didn't want to use the tissue that was important to the diagnosis, so these were central regions of mastectomies. But once we established that, we established a protocol, established that we could see contrast, we moved forward to do a diagnostic accuracy study, an initial diagnostic accuracy study on 90 patients, where we had 71 patients in a reader study and 19 in a training set. We scanned mainly two margins within a time frame of 50 minutes. So we're not trying to demonstrate here a clinically ready tool. We just wanted to see in a small set of specimens if we could correspond tumor with the clinically relevant outcome. So for that reason, we didn't try and scan all the margins. We scanned two, and then we match with the pathologist and the different tissue types. And we then performed a blind reader study on 7 readers, combination of surgeons, radiologists, and pathologists, and also an engineer. So here are 2 images which are representative images from that study. In this case, we can't determine how the histology is performed. They perform cross-sectional histology, which is in the plane that's orthogonal to our en-face view. We like to look in the en-face plane because we can see over the largest field of view. Also, this is the plane where we don't perform the axial fitting, so our resolution is highest. But we do scan through the OCT B scans to make sure that we've got the corresponding slice, and we then place this red arrow or this red line, which corresponds to the region from which the histology corresponds. In this case, we can see a large region of invasive tumor with adipose either side, and that corresponds well with what we see here. We've got elevated stiffness where the tumor is. This is a benign case where, again, we've got relatively low elasticity. We can see some of these artifacts coming out at the boundaries of regions, but by and large, it's low elasticity throughout this region. And so we trained our readers on these images. We had a training set where it was a very simple reader criterion based on 1 or 2 simple parameters from the OCT and the elastography images. So these are the results from the readers. Importantly, we had the ability to do OCT only, first of all, train the readers to just read the OCT because we've got that data anyway. We then transposed the images, mixed up the order, and a couple of weeks later got them to read the elasticity. And we were able to kind of streamline this data to see the effect of OCT only, OCT plus the elastography, and then also just the elastography on its own, this quantitative microelastography. We assumed that if we combined OCT with elastography, we'd get the best results. And we certainly got a much better outcome with combining the techniques than we did over OCT alone. Using just OCT, we got results that were similar to what others had got from using OCT, sensitivity and specificity of around 70 and 80%. That increased to around 80 and close to 100% when we incorporated elastography. But when we just looked at the elastography reading, so we just look at the elasticity decision, we got a sensitivity and specificity of 93 and 96%. The reason for this, I believe, is that there was an aspect of the OCT reading that so we said if the OCT signal decays with depth in a certain way, it's likely to be tumor, and that was difficult for readers to interpret correctly because to determine if the signal is decaying or if it's noise was tricky. So we still believe that the combination of these two is probably ultimately going to give the best result. And maybe we need there's a technique called attenuation imaging in OCT where you quantify the gradient of the OCT signal with depth, and we've published a paper on that. And if we incorporate that image as well as the elasticity, we think we might get the best outcome. So all of what I've spoken about so far has been on the benchtop, not on the specimen, but we've been collaborating with surgeons from very early on in the piece, and this main surgeon we work with here in Perth was adamant from the start that really what we would want is a handheld device in the surgical cavity. Scanning or identifying where the tumor is on the specimen is really a surrogate for what's left in the cavity. even if we can determine where the cancer is with 100% accuracy on the specimen, it's a whole other ballgame to try and spatially locate the tumor from that specimen, because the sample is very malleable, it's very soft, and so when the surgeon goes to re-excise, or even if it's during the surgery, they go to excise the remaining cancer, they typically will have to excise much more tissue than the extent of the tumor, just because there's a large degree of uncertainty as to where the tumor is. So for that reason, we also have been developing this handheld elastography probe, which is clinically potentially much more useful, technically a lot more challenging because of motion artifact, which degrades both the OCT signal, lead to blurring of the image, but also we've now got a variable mechanical load, because any motion of the user's hand or the patient leads to a variation in the deformation that we're applying. So our strategy to overcome that has been just to image as fast as possible. So we developed a new scanning protocol, which allowed us to scan that volume in around 3 seconds in the results I'll present here. And we're hoping to get that to below a second. So basically that allows us to scan faster than the majority of the motion caused by the user and the patient. So I'll show a video of one of the first scans that we performed. It's pretty explicit, so just warn you about that. But we put this, we sterilized the probe, and also put this surgical sheath on it as well, a requirement in the hospital that we're based in. So the surgeon removes the cancer as normal from the patient. We've now got our cavity. The surgeon then looks at the intraoperative X-ray, identifies a region where it's potentially cancer, places the probe in the corresponding region of the cavity. The actuator is now incorporated in this device, applying the deformation to the tissue. We have the scanning live. The surgeon was only really making sure we had contact with the tissue. After the surgeon has performed the scanning, they excise a region, a shaving of tissue from where we've scanned, and mark the cavity side, so that when in post-operative histology, we're able to correspond our in vivo image. We have a co-registration with histology, so we can validate what we found. The image quality definitely takes a hit in these early scans, but we can see that the contrast that we've seen ex vivo is coming through. We see elevated elasticity here. So in this case, it was the corresponding margin from the specimen that was excised was positive. This is the in vivo result showing that elevated stiffness. So it implies that we've scanned tumor here. And in this case, there was no tumor in the corresponding margin, and it's relatively low elasticity. So I think scanning faster below 1 second, also increasing the amplitude of the deformation in the PZT stroke will help to improve these images. And we've now scanned around 21 patients and are really still just setting up the protocol to hopefully repeat the kind of accuracy study we performed on the specimen. So in the last few slides, I wanted to talk about applying this technique to scanning on the cellular scale. And really I'll show results from a system with about 5 micrometers resolution optically, but we've developed a system that has sub-micrometer resolution as well, which we think will greatly increase the ability to see not only cellular scale, but actually intracellular components, intracellular elasticity. As a first kind of preliminary experiment, our collaborator, Yusuf Choi in UWA, wanted to look at the effect of TAS activation on the stiffness of adipose-derived stem cells. So TAS is linked to increased proliferation and increased spreading. It's linked with cancer cell metastasis and tumor development, and it's, I think, in the literature been implied that it leads to stiffening of the tissue, but it hasn't really been shown in 3D. So initially we encapsulated our cells in GELMA, and first of all looking at just GELMA hydrogels. Then we looked at the adipose-derived stem cells, unactivated and activated. So as a baseline, we have in blue here the GELMA, where we see this peak at around 3 kilopascals. When we look at the adipose-derived stem cells, we see we've got this double peak, where we've now got the peak from the GELMA, but also the stem cells. With the TAS activation, we see that there's not only an increase in the stiffness of the stem cells, but also a larger variation in the stiffness of individual cells. In this initial study, we were able to look at the stiffness that corresponded to each cell. We're not really at the subcellular scale here. It's kind of, we're getting a global measurement of elasticity from each cell, but we were able to visualize that and to kind of try and start to get an understanding of how the structure of the cell from OCT, illustrated here in grayscale, corresponded to the stiffness. But yeah, we think this is a promising direction and promising preliminary measurements. But really, when we increase the resolution, combine that with some of those computational approaches to be able to look at subcellular components, it could be quite a useful technique in some applications in mechanobiology. We feel the advantages are to be able to look in 3D. We can look we can perform this imaging in a matter of 3-4 seconds. And we're also able to look at fairly large spatial fields of view. But just to summarize, spoken a lot about our compression-based OCE technique, which we call quantitative microelastography. We're mainly focused in 2 areas to develop applications for surgery, initially in breast cancer and also in mechanobiology. From a technical perspective, our main developments ongoing are these handheld probes. We really want to get the same image quality from the probes as we have on the benchtop, and also, as I mentioned, then to try to go to really high resolution elastography. By now that we understand how the spatial resolution is formed, we really need to go after each aspect of that. So we're looking at improving the OCT resolution or OCM resolution, the signal processing. So we're looking at detailed analysis of speckle to try and understand how we can reduce the range over which we perform the linear regression, and also, probably most importantly, the mechanical deformation, and using that inverse elasticity solution, for example, to try and greatly reduce or greatly improve the spatial resolution. So that's everything. So thank you very much for listening, and I hope that was useful. And if anyone has any questions, I'd be happy to try and answer them. Thank you.
Great. Thanks, Brendan. Great talk. I guess I'll kick off with sort of 3 questions first that Chen and I have been looking at. The first one will be, you talked about iterative solution to try and improve the readout. Will this iterative process also accrue inaccurate estimates in terms of smoothing?
Thank you, Steve. Yeah, that's a good question. And the answer is it very well could. If we go back to the slide, really, so what you rely on is that the inverse problem is well posed. In other words, that there's one unique solution to it. So in our nice easy cases here where we've got silicone phantoms, that's probably the case. But in complex breast tissue, it may not be. We performed this originally on the version when we just have the axial component of displacement. That increases the likelihood of errors because we don't see the full picture. So we think incorporating the 3-dimensional 3 components of strain with this will reduce will constrain the problem sufficiently enough. But I think the key point is that if you were directing the question towards breast cancer, I would say it would be very difficult because it's such a complex tissue. If we're talking about mechanobiology, where we've got relatively uniform hydrogels with cells which the stiffness is on the same order of magnitude normally as the gel, I think it will be it can be well posed, and we can get accurate solutions, so not introduce more inaccuracies. But that's to be determined.
Well, yeah, that's actually a great answer in the sense that it leads to the second question, which is that you're shown live, well, not necessarily live in vivo elastography, but sort of excised on the procedure operation table. And so if you think about it, would it be possible to conduct this in vivo? And if it does, would blood flow in a live tissue complicate the readout?
It's a great question. And actually, I didn't present it here, but from the in vivo data, we actually made a map of the microvasculature in the cavity. So we did that for the reason that if we can identify where the blood is, then we can account for it. So I think the biggest impact we've seen of blood is actually just blood dispersed on the surface of the tissue from an optical point of view, attenuating and mucking up the beam. So we irrigate the cavity with saline to try and reduce that effect, but that's definitely, as with all optical techniques, that can be problematic. But in terms of how it disrupts our mechanical deformation, we haven't seen too much evidence of it. And I think the reason for that is that effectively the blood that's constrained within a vessel will act like a solid material,
Right.
because it's incompressible and constrained spatially, so it leads to deformation. What I'm concerned about is that it might lead to an elevated stiffness that we misinterpret as tumor. But that's the reason why we wanted to map the microvasculature, so that we can identify where they are, so that we won't be misled by the elasticity measurement in those locations.
Great. There's a question from Yurika on. She's envisaging that OCE might be a useful tool for R&D or prosthetics. And what's your take on it?
On prosthetics, I think it would depend on the exact.
I could maybe explain a bit.
Yeah.
I could maybe explain
great.
a bit. So a friend of mine, he works for Otto, which is a very big company. Like they build all kinds of prosthetics, and usually it's so when tissue or whatever kind of grows on hard surfaces, it changes its mechanical properties. And I think there's a huge R&D field out there, like research and development, where they actually try to make sure that these kind of metal structures or whatever, kind of like a hip or whatever, is as compatible with the human tissue as possible, such that it can be also used as long as possible. So I guess there the demands might also be quite high, at least in that field, to study how the mechanical properties of cells in contact to metal surfaces also change, or to whatever kind of ceramic surfaces or so. That's why I was only thinking, because he only told me that there's quite lots of research going on in that field as well, and I just thought.
So definitely, I think that's. I'm not a mechanical biology expert per se, our collaborators are, but I think the field has shown that there's a big difference in the response of cells depending on if they're in 2D or 3D and if they're on a hard surface or not. So we feel that we have an advantage in that we can see potentially in 3 dimensions. AFM, for example, is limited to 2D, and so definitely if we can improve the resolution so that we can really see the different components of the cell's elasticity as well as the material that it's embedded in, then it could be useful in that regard. But it's not something we've looked at too much until now. Maybe I should look at more. Thank you.
So everyone, welcome to unmute and ask questions directly to Brendan. If not, I'll ask the next question that I had in mind was, it's based on OCT, which is currently a displacement measurement. Doesn't mean that I'll just buy an OCT and I will be able to conduct that in any lab. That's one. And how translatable are the in terms of the computational tools you have to other imaging methods?
Yeah. So the first question, Steve, is the answer is that we currently we're building the high-res system ourselves in the lab because it's difficult to get that commercially, but we've reverted to mainly using commercial systems. Most of our systems are from Thor Labs, so the only technical adaptation you need to make is to synchronize your actuator deformation with the acquisition of the B-scans, but that's straightforward. You can basically just take a line from the camera acquisition and synchronize, just even from with a standard signal generator, you can synchronize the actuator in that way. And a number of labs, we're working with a number of labs to try and give them the ability to do this imaging. I think the biggest challenge is probably, and for us, I think as well at the start, the biggest challenge was probably, we're optics people, right? And trying to understand how to set up the mechanical system. It's actually straightforward, but it's all the kind of fine detail, like friction can cause problems. So if you've got a large degree of friction between your sample and the compression plate, that can limit the ability to deform your sample. So we've needed to address a bunch of issues like that, but there's nothing special to what we do. It's just fine detail and the experience of doing it. But we're really keen, obviously, for other labs around the world to use it. So very happy to team up with people and to work with.
Cool.
The signal processing side is linear regression, so it's not complicated.
Right.
Then your second question of could you use other optical imaging techniques? Absolutely. I mean, if we look at the original slide, it's just you need to measure deformation somehow. So we've even developed simple techniques where we've just published a paper using a smartphone where we track deformation using a digital camera. So certainly digital holography, for example, and people have, I think initially Amy Oldenburg a number of years ago looked at doing elastography with holography. But the issue with applying our particular technique to holography is that we rely on the depth section. So we need to have depth to measure that strain. So techniques where you don't have too much depth imaging may be more suited to the wave-based approaches, where you track the deformation across the surface of a sample, for example, and extract the elasticity in that way. And I think that's where holography has been utilized in elastography.
So we have a question from Tom Cox. His question was, the extracellular matrix is not considered as a linear elastic material and can exhibit more complex mechanical behaviors, including viscoelasticity, mechanical plasticity, and nonlinear elasticity. How do you cope with that in vivo in situ? In your
great question.
Yeah.
Thanks, Tom, for your question. So I think we've developed techniques to measure viscoelasticity and nonlinearity as well. And I think certainly clinically, it's a case of we need to make sacrifices. We've got a certain amount of time, so we don't have the time to fully characterize the tissue. So I think that the real answer is that the viscoelastic response is quite slow in tissues, and at least the creep deformation, which is kind of how viscoelasticity manifests in our version of the technique. So over the time that we perform our imaging, the viscoelastic effects are quite low, so that we may have a slight inaccuracy in our elasticity because we don't know where we are on that creep deformation curve. But within the acquisition time, there won't be too much variability of viscoelasticity. So in that way, we're only really concerned with kind of absolute contrast, so that it doesn't affect us. The nonlinearity can affect us. So depending on how much you push, if you push the probe more or less, you definitely can stiffen the tissue, as it were. But we've seen that over the range of deformation applied by the surgeons, it's fairly consistent. And we believe that's because in breast tissue, it's fairly linear in the deformation range of around 0 to 20% strain, so it hasn't affected us too much. But when we're on the benchtop for the mechanobiology applications, for example, there we have much more time, so we can build a much more complex acquisition protocol and processing algorithms so that we can have a more complete picture. So that's certainly something that we plan to expand our prior work on those mechanical properties, expanding that to our more current.
Cool. I guess there's sort of three technical questions from Eureka and Chen. The first one from Eureka is, can the adaptation of the two be accelerated? I guess what's necessary to accelerate it into clinics? The other two technical questions from Chen is, axial resolution, are there possible methods to improve axial resolution? And the second one would be, blinder readers on the mechanical can get better results than OCT plus QME. Does it mean that QME itself is enough? Yeah, sort of, yeah.
Maybe I'll take the last question first. So certainly from our study, it implies that that QME is better, but that was a fairly small study. It was 90 patients in total. It was on the excised specimen. So, and also we were looking at specific regions of the tissue. So if we start to try and roll this out to be, used on any specimen at any time, I think you want to have all the information you can have. We learned from that study, I think, how we could adapt the presentation of the data to a reader. And also we've started to look at machine learning to try and crunch through the data to get better results. And we strongly feel that the OCT definitely has a role in providing a more robust solution. And I think a large part of it is to look at to map the attenuation coefficient. So OCT is a grainy image. It's difficult to see exactly where structures start and end. But if you map the attenuation, that's correlated quite closely, I think, with tumor. So we think OCT will have a role. The working backwards axial resolution, and can we improve it? I think was another question.
Yep, that's all right. Yeah.
So yeah, again, the three components of axial resolution are the OCT system. So if we go to higher resolution, we make the speckles smaller. When the speckles are smaller, we can proportionally reduce the fitting range. So that's one way to improve the system resolution. Again, it's the dark speckle that limits our ability to accurately do that linear fit. We've just published another paper where we're looking at speckle, and we're looking at the inaccuracy of phase sensitive detection brought about by dark speckle itself. And so I don't know if people are familiar with speckle reduction. So in OCT, there's techniques where you can generate or gather a number of images, each with a different realization of speckle, and they basically incoherently average them together to increase the image contrast. We could utilize similar speckle reduction techniques where from each realization of speckle, we have an accurate measurement of displacement where there's a bright speckle. So if we kind of compound a number of speckle realizations, extracting our displacement only from the bright pixels and put them together, I think that will dramatically increase the accuracy of the axial resolution, but it requires more data. So again, we have the trade-off. And then ultimately, I think the mechanical deformation, again, with the inverse elasticity solutions or variants of them can dramatically, that it basically reduces the mechanical assumptions we need to make. And we've seen that that's made a much sharper transition between mechanical features. And then
and Yurika's question on adaptation, how can we get this all to the clinics? I guess you've proven that takes the first step, but what are your experiences on that?
Yeah, well, from our perspective now, we've scanned 20 patients in vivo, and there's a big jump from scanning a specimen to scanning in vivo. So we think we're on top of the 20 patients we've scanned has brought up a number of issues that need to be resolved. So for example, we need to apply more deformation, and we need to account for angle of the probe. So we're working through the technical improvements of the probe. And then ultimately it's going to be, what does in vivo breast tissue look like mechanically? I don't think anybody knows that. So we're going to probably have to perform another study where we're just looking at, okay, what does the tissue look like now? We've got some insight into that from the patients we've scanned, but once we've got a robust second generation version of this probe, I think we'll be able to go after that. But so in terms of, I'm not sure how to accelerate it, but we're just trying to methodically work through each of the steps to try and address it. The other thing I think would be to look at other tissues, actually, Ulrike. Like we've only looked at breast tissue, and that's a very complex tissue. There are potential applications in brain surgery, for example, and a bunch of different other clinical applications that we haven't looked at. It might be that there's a more straightforward application somewhere else that we haven't looked at.
I see. Cool.
Brandon, I have one more question, Steve. So,
yeah, go ahead.
So can you give us an idea how fast the measurement of OCT can be done in the clinic application?
Yeah. So in the systems that we've got, the A scan rate, so the line rate is 250 kilohertz. So that's the speed of of one depth scan. So then it's a case of how you construct your acquisition protocols. So typically you want to Nyquist sample the optical resolution. So we've relaxed that a little bit so that we can scan faster. So we're trading off resolution against scanning field of view against scan time. So in our current case, we've got a resolution for the in vivo probe of around 15 microns, and we can scan an 8 by 8 millimeter by 2 millimeter volume in around 3 seconds. we've figured out a way to increase the to reduce that to around 0.9 seconds. So that's the kind of scan rates we can get with our system. The 250 kilohertz A scan rate is really the rate determining step for OCT. That's the ultimate limit on speed. And I mean, you can get off-the-shelf systems in the megahertz range now. I think there's a company in Germany who's Optores who sell a 3 megahertz laser, but it's quite a big FDML system, and it's more expensive than we thought would be kind of, from a commercial point of view, viable. So and the other consideration is probably the mechanical deformation. You need to be careful at the rate at which you're deforming the tissue. So probably ultimately, I think you can probably get this down to around 0.5 second with a clinically meaningful image.
That's cool.
Great.
Thank you.
Yeah. So I guess, does anyone else have any more questions? I get it's quite late now on your end in Virginia, and I guess for us it's time to go to work, and Brandon needs to probably take a nap before he
I need to go give a lecture. I've got a double lecture at 9, so I've got time for a cup of tea.
Oh, cool. So if I guess there's no other questions, I really appreciate Brandon's time this morning, giving this fantastic talk. I hope everyone who was on the call really enjoyed it. I personally have. So thank you all for your time, and we would be posting the first videos quite soon, and obviously the second video as well on a special dedicated YouTube channel.
Hope to see everyone in our next talk, which will be on May 25th.
Yes. All right. Thank you, everyone.
Thanks, Steve. Thanks, Jen. Thanks,
Thank you,
everybody.
Lecture.
Bye.
Bye-bye.
Bye.